For centuries, astronomers have looked up at the skies. Their goal is to find out how the universe works. They observe planets, stars and galaxies and the dust and gas that surrounds them. The telescopes that astronomers use have traditionally operated in ordinary visible light, which can also be seen by the naked eye. But over the last 100 years, they have started to use instruments that can see other parts of the spectrum, at radio, infrared, ultraviolet and X-ray wavelengths. The Netherlands has played a leading role in the development of radio astronomy. In the 1950s, Dutch astronomers and engineers built what was for a brief time the largest radio telescope in the world. The 25-meter dish that still stands outside Astron's headquarters in Dringelo was used to study cold hydrogen gas in our galaxy. In the 1960s, Astron built the Westerbork Synthesis Radio Telescope. The 14 25-meter dishes of this telescope working together allowed astronomers to look deeper into space and see more detail than was possible with the single Dringelo dish. The Westerbork array has played a crucial role in the study of cold gas in other galaxies, which demonstrated the existence of dark matter. Since the early 90s, radio astronomers from all over the world have been preparing for the next big step, to construct a huge new telescope, the Square Kilometre Array. The SKA will be built in either South Africa or Australia. In order to make such a large step in collecting area, and therefore in sensitivity, new technologies have had to be developed. It has driven the design of small antennas that do not move, and can be steered digitally, rather than the conventional dishes. Astron, which has been closely involved with the SKA project from the start, has led the way in developing this technology. Out of these plans, LOFAR, the low-frequency array, was born. Instead of building a single large telescope, LOFAR makes use of the same concept employed in the Westerbork array. Signals from a number of small antennas spread over a large area are combined, resulting in much sharper images. In LOFAR's case, the antennas in the Netherlands are grouped together in 36 stations, half of which can be found in the municipality of Borger-Odorn, between the villages of Exlo and Bouwnen. As part of the LOFAR project, this core area has been developed as a nature reserve. This unique combination of high-tech and ecology has provided a quiet environment where astronomical observations and natural beauty go hand in hand. At its heart, the central Superterp is located, which hosts 6 stations. Each station has 96 low-band antennas and 48 high-band antennas. Geophones and infrasound sensors can also be found on many LOFAR stations in the Netherlands. All signals are sent through a high-speed glass fiber network to a central processing facility at the University of Groningen's Computer Center. The development of LOFAR has helped engineers prepare for the challenges that lie ahead with the SKA. But LOFAR has also been constructed to shed light onto important questions that astronomers are eager to answer. Because of the way LOFAR has been designed, it can see large areas of the sky at once, making it an excellent survey telescope, looking deeper and sharper than ever before at these frequencies and searching for unknown and rare radio galaxies, clusters and quasars. Instead of moving the telescope to point in the desired direction, LOFAR's antennas are steered electronically. This process is referred to as beam forming and can be done for many directions at the same time. It is through this technique that LOFAR is able to observe such a large part of the sky at once. The beams are formed in real time using the electronics housed in a cabinet on site at each station. LOFAR's ability to map out large areas of the sky will also help it look for variable radio sources, discovering countless transient objects which go off once or perhaps more often. LOFAR will also contribute to the study of pulsars, which are cosmic laboratories where Einstein's theory of general relativity can be tested. Many new pulsars will be discovered in our own and hopefully also in nearby galaxies, and studied in ways that are not possible with other radio telescopes. Cosmic particles, with energies over 1 million times higher than can be produced in particle accelerators on Earth, collide with molecules in the upper atmosphere and give rise to a shower of charged particles which produces a short radio pulse. LOFAR has also made a major contribution to this area of research, and will continue to do so, hopefully telling us what kind of cosmic sources produced these most energetic of particles. Magnetic storms from the Sun can interfere with radio communications and damage satellites orbiting the Earth. These events can be studied with radio waves which can be picked up by LOFAR. LOFAR will also be used to investigate the role of magnetic fields in galaxies and clusters of galaxies. After the Big Bang, the universe went through a period that is referred to as the Dark Ages. One of the most exciting discoveries that astronomers are hoping to make with LOFAR is to find an answer to the question: how did the first stars and galaxies form that turned on the light in the universe? But we also know that new instruments lead to new and unexpected discoveries. So perhaps most eagerly awaited are the results we haven't yet thought about. Early on in the project, it was realized that other sensors could also be attached to the LOFAR network and the powerful central computer that processes the signals. Contacts with geophysicists led to plans to add geophones and infrasound sensors to the network. The geophones will be used to study seismic activity resulting from the production of gas from reservoirs in the north of the Netherlands. The infrasound sensors measure small changes in air pressure which can be caused by volcanoes, large explosions, or planes breaking the sound barrier. Infrasound monitoring is also one of the verification techniques for the Comprehensive Nuclear Test Ban Treaty. The idea of distributed sensors with central processing of the data was also taken up by agricultural scientists. As part of the LOFAR project, they have investigated how these concepts can be used in farming. The focus has been on developing new techniques that can help prevent disease, promote animal welfare, and provide support to the farmer in deciding on when to use fertilizers and pesticides. Every second, LOFAR's antennas produce nearly 10 terabits of data, equivalent to 265 full DVDs. Much of LOFAR is therefore only possible thanks to the latest achievements in information and communication technology. An IBM Blue Gene supercomputer, originally developed for massively parallel computations of biological processes, forms the digital heart of LOFAR. The Blue Gene concept was especially adapted for LOFAR's streaming data concept. After initial processing, the data is exported and archived in Groningen, Amsterdam and Jülich in Germany. Through collaborations with the Big Grid and Target projects, a distributed archive is being set up. With data rates approaching those of CERN's Large Hadron Collider and unique and time-variable access patterns dictated by the scientific users, LOFAR is leading the way as an operational e-science infrastructure. LOFAR stations are not just being built in the Netherlands. They can also be found in Germany, France, the United Kingdom and Sweden, possibly more in the future. Each country has gathered its own funds to pay for the construction and operation of their stations. All signals are also sent through fibers to the same central processing facility in Groningen and combined with data from the Dutch stations. Just as in the Netherlands, astronomers in these countries have ambitious plans for unique observations that will be possible with LOFAR. To make LOFAR a truly European instrument, the Netherlands and its partners are to take joint responsibility for the operation of the International LOFAR Telescope. Sensing the universe, the Earth, and our surroundings.